This video, we're going to continue talking about E and where we can see some applications of E. So remember we have this PERT formula, which happens anytime I see compounded continuously. So I'm going to use my formula here to answer this question. So what is the total amount? So remember that's A, that's what I'm looking for an investment of $500 invested at 5.25% for 40 years compounded continuously. So we're looking for A, my initial investment or principal amount is 500 times E. This is a decimal is 0.0525, so that's my rate. And then times T, which is 40 years. Okay, use my calculator here to punch that in. So we have 500 times E raised to the 0.0525 times 40. Okay, so we have $4,083.08. $4,083.08. So that is the amount that is now in that account. Okay, so now we're going to look at what happens if we don't have the rate. So in this instance, we're actually going to have to find the rate first. Okay, so we have the George River herd of caribou in Canada was estimated to be about 4,700 in 1954. It grew at an exponential rate to 472,000 in 1984. So we need to figure out what was that growth rate that happened over that amount of time. So here's what we're going to do. We're going to look at the initial amount. We're still going to use this here. Okay, so the initial amount of caribou was 4,700, okay? And we're kind of going to treat this as the initial and the new amount to help us find the rate. So I started at 4,700 caribou, okay? We're going to use this PERT formula to model population, okay? Anytime we hear exponential growth, we can use this, especially if I don't know the rate, because I can find that. So I'm going to leave this as R. I don't know the rate. Now time, so after a certain amount of time, right, I started at 4,700 and I ended up at 472,000 caribou. So after how much time did that happen? Well, I just need to do 1984 minus 1954 to get 30. So 30 years after starting at 4,700, I ended up at 472,000. So I am now going to solve this for R. So here's what I want to do first. I want to get the exponential piece by itself, so the E raised to the 30R. So in order to do that, I need to first get rid of this 4,700. So we're going to divide. Okay, and you can leave it as a fraction right now, or we can go ahead and do the division. Let's see here if it works out nicely. Yeah, this one doesn't work out nicely, so I'm going to actually leave it as a fraction here for right now, you guys. I'm like to do all the calculator stuff at the end just to get the most accurate answer. So we're just going to leave this as a fraction. So I've got 472,000 over 4,700 equals E raised to the 30R. Okay, so now I want to get R by itself. So I need to get rid of the E and then get rid of the 30. So we're going to get rid of the E first by applying natural log to both sides. So I'm taking natural log of this whole thing. Again, I'm not simplifying just yet, but I know natural log and E will cancel. So now I have natural log of 472,000 over 4,700 equals 30R. So now to get R by itself, we would divide by 30. So this whole expression is going to equal R. So I'm going to type that in now all together one time so it's more accurate, only rounding once, not rounding all the way throughout the process. So we're going to take natural log of 472,000 divided by 4,700 and then divide by 30. So it's with this, you guys, I would recommend rounding to a minimum of 3 decimal places, if not 4. So this is my R. So R is approximately, and we're going to typically be rounding here. That's okay, but like I said, go a ways out so it's more accurate. So I'm going to go to 4 decimal places. So I'm going to do 1536. Okay, so minimum of 3. I think 4 is actually even better. So we're going to do 4 here Okay, so we figured out the growth factor, right? So this was part A. Figured out the growth factor or growth rate of the herd, okay? Now it says if the herd had continued to grow at the same rate, so this rate that we found, okay, about a 15% rate, what would its population have been in 2010? Okay, so now for part B, we're looking for total population, so that's our A. So what's the new population, okay? Initial amount is still, we're gonna use that very first point we talked about, the 4,700 caribou. Okay, we're now gonna plug in that rate we found for part A. And then I need the time. So now we're talking about 2010 to 1954. So we're gonna do 2010 minus 1954. So the total time we're talking about here is 56 years. So if it continues at this rate, 56 years, what's our new population? I'm just gonna remind us where we got that number from for notes purposes. Okay, and then again, you can just plug that into your calculator. So we're gonna go 4,700 times E raised to the 0.1536 times 56. All right, so we have, if the population continued at that growth rate, this is how many caribou, 69678. So 2,500,000 about, okay? And I could probably round this up to 9, talking about whole numbers. So that's how many caribou there would be if it continued at that same growth rate. Okay. This is a really common thing you guys will hear about as well in this unit, an application often used, found in chemistry. But the half-life of a substance is the time it takes for half of the substance to break down. And this is often, almost always, an exponential equation. I actually don't like that this is introduced to you guys. So I'm actually just going to write it as our PERT formula, but reminding you that this has to be negative if it's decaying. So we have a substance and it's decreasing exponentially, which is why there's only half of it remaining. So this is the same equation, you guys, different variables, and I think that can be confusing. So I want you to focus on using this guy. Okay. All right. There we go. Okay, so here's an example of a half-life problem. Plutonium-239 has a half-life of 24,110 years. So what that means is it takes that long for it to decay to half its original amount. How long does it take for 1 gram sample of plutonium-239 to decay to 0.1 grams? So this one's actually going to look a lot like the caribou problem. I have to find its decay rate first before I can answer the question. So I'm going to say must find decay rate first before we can answer, okay? So here's how we're going to do that. So I'm going to use the half-life to help me. So it actually doesn't matter what amount you use. I kind of like to think of percentages, but you can actually use any number you want. So I'm just going to use 1 for the sake of it. Let's say I started with 1 gram, this is what I'm starting with anyway in this problem. So my initial amount, right, so I'm using this guy. Okay, so I'm going to use my initial amount of 1 gram. So 1, e to the r, and you can either do negative r or r here, it doesn't really matter. We just have to know that r needs to be negative if it's decay. So I'm actually just going to put it as r here right now, you guys, and we'll see what happens. So time, well, it took 24,110 years. And then how much was left after that? Well, half the amount. So if I started with 1 gram, a half would be left after that time. So now I'm trying to get E by itself. Okay, so if I divide 1/2 by 1, right, we still have 1/2 or 0.5 equals E raised to the 24,110 r. Okay, so now I need to get rid of e, so we're going to take the natural log of both sides. So natural log and e cancel. So I have natural log of 0.5 equals 24,110 R. So we're divided now by 24,110. So R is equal to this amount. Again, this is going to be a decimal, so I'm going to approximate, and we are going to round. Let's do 4 decimal places again. So I've got natural log of 0.5 divided by 24,110. So remember when you see this, you guys, if it's negative, it's telling you the decimal moves left that many places. So I move my decimal left 5. Okay, so that means I have 4 zeros in front of the 2. So we have negative. So see, I should get a negative answer here. So I have negative 1, 2, 3, 4, 2. So oftentimes these ones, you guys, we got to go out further than 4. So we're not just saying our rate 0. It's got to be something like that. So I might even go one more and say 2, 9. We'll round. Okay. All right. So now we know our rate. So now we can answer the question. How long does it take for this 1 gram sample to decay to 0.1 grams? So now we're asking how long. So we're looking for T. So my new amount is 0.1 gram. I started with 1 gram. We know the rate is negative 0.000029. Okay. And then we don't know T. So we're looking for T here. So same thing, my variable is in the exponent, so I got to get T by itself. So again, I can divide by 1 first, that doesn't change anything. And then we're going to take the natural log of both sides. So natural log of E will cancel, so I have natural log of 0.1, negative 0.000029, and then divide. So then T, if I do natural log of 0.1, and then I divide by negative 1, 2, 3, 4 zeros. That's how long in years, right? Time in years it will take for this to decay. So we're going to say 79,399, almost in a half, right? So that's how long it would take 1 gram to decay down to 0.1 grams. Okay, one more example here. Determine how long it will take for a 650 milligram sample of chromium 51, which has a half-life of about 28 days, to decay to 200 milligrams. Okay, so again, I have to find the rate at which it's decaying first. Okay, so we are going to, again, use the half-life. So we're starting with 650 milligrams, okay? And half of that, right, if I do 650 divided by 2, is 325. E to the R we don't know, right? And it should be negative when I solve for R because it's decaying, and it took 28 days. So something I need to remember is my unit of time right here is not years, it's days. Okay, so now we're going to solve for R. So here's something pretty cool about half-life. So you guys, as soon as I get this exponential by itself, this number will always be a half. It will always be 0.5 when we are putting in the half-life time. So if you don't know the original amount, it's actually okay. You can just always put 0.5 over here and then E to the time, the half-life time, times R. So that's just kind of a shortcut. If you don't remember that, that's okay. You can still start with that initial setup. So now I'm going to take the natural log of both sides, get rid of E. Okay, so I get natural log of 0.5 equals 28R, divide by 28. So I have natural log 0.5 over 28 is equal to R. So our R is going to be approximately, here's where again I should get a negative number. So natural log 0.5 divided by 28, negative 0.02476. Okay, go a few decimal places there. And now we can look back at this question. So it's saying how long will it take, so again, solving for T, for an initial 655 milligram sample to decay to 200. Okay, so 200 is my new amount. We started with 650. E, we now know our rate is this number here. and then we're looking for how long, so we're looking for t. So again, get the exponential piece by itself first, so divide by 650. Okay, I'm just going to leave it as a fraction for now. Okay, so I have 200 over 650 equals e negative 0.02476. Now I take the natural log to get rid of e. Okay, and then divide to get t by itself. All right, so t is equal to this whole thing, so we're going to do 200, sorry, lost my natural log of 200 divided by 650, and then that whole thing divided by negative 0.02476. All right, 47.6, and remember our unit of time here was days, not years. So whatever unit of time we use to find our rate needs to be that same unit of time here. Okay, so there's some examples of exponential decay, specifically half-life.